All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna continue learning some Rust stuff. Not necessarily the Rust basics, but there was some stuff that I came into yesterday. Some stuff that I um, got into yesterday. Some research that I got into yesterday, which kind of led me down this path. So I was looking in actually in yesterday's stream, I think I'd mentioned that I was curious if there were any Rust-based agent libraries. I'm not even sure how to say that. So like Google has this thing called ADK, which is the Agent Development Kit. It lets you create agents that would then perform certain tasks, right? It allows you to create an essentially an agentic workflow, and a lot of it is being used for AI related stuff to create sort of an autonomous workflow. But I was like, okay, first of all, isn't it possible that it could be used for something else as well? Like if the idea is for it to be autonomous, then maybe it is being used for something else as well. Like I recently came across the concept of agents, right? But I'm sure agents were being used in some way, shape, or form previously as well. So that got me. And well, another thing that got me to do research was ADK is a Python-based toolkit, a Python-based library. So I was like, okay, one exists on the Python side. What about on the Rust side? I'm sure more exists on the Python side as well. But yeah, what about the Rust side? So let me look it up, and I did find a couple. One of them was called, I believe, Auto Agents, if I'm remembering the name correctly. I think that's what it was. Auto Agents, and upon doing more research on, actually, you know what? I could just open it up and show it to you guys. Uh, I don't know. I don't know if I should do that here because the system might get stuck again. Also, we might be having some network issues. You know what? While the network issues get resolved, because we seem to be actively losing frames, while this issue gets resolved, let me go load up those two repos that I want to show you guys. Why is it on this? You're joking, dude. Come on. Okay, what is being loaded up here? Oh yeah, okay, you guys were just seeing the okay, okay. Right. So let me open this thing up there and then Rust auto agent, or I think it's agents. Yeah. So there was auto agents, and auto agents is apparently built on top of another framework, which is what I decided to dive deeper into. That framework is called Ractor. Um, it's a Rust-based framework for actors specifically. I forgot exactly what that concept is called. I'm gonna open the thing up and show it to you guys. And I found that really interesting. As I was reading up, so I obviously decided to have a conversation with Gemini about it. Oh God, my thing is freezing again. Okay, we shouldn't be opening up all that many things here. Okay, yeah, Ractor is a pure Rust actor framework. So this is what got me curious. I was like, okay, if Auto Agents is based on this, if Auto Agents is built on top of this, and this is an actor framework, then maybe I could use this concept of actors for something else as well. So let me show you guys the thing here. Let me switch away from BRB. Okay, so this is the auto agents repo. This is, as it says, a modern multi-agent framework in Rust. Okay, so it says Auto Agents is a cutting-edge multi-agent framework built in Rust that enables the creation of intelligent autonomous agents powered by LLMs and Ractor. This is what got me to check out Ractor. So I went and looked at Ractor. This says that it's a Rust actor framework. Um, yeah, this it said that this is a Rust-based actor framework. So because I had never really heard of the concept of actors, or maybe actually I can't remember if I did hear about this concept before and I just don't remember it. But I don't think I ever dove into the concept of actors. There might have been one specific, I can't remember what it was. It was something game dev related, I think. I can't remember. Or maybe it was a thing um in Unreal Engine. Maybe actors are a thing in Unreal Engine. I can't remember. But I was like, okay, since I don't know anything about this, let me try having a conversation with Gemini about this. Um, I'm gonna read the thing out to you guys, and I'm actually gonna be exploring this a lot more, because yesterday I was discussing the whole, workflow of yesterday. I think in a stream before that as well, I'd been discussing the workflow that I want to set up um, for my stream AI voice app. Give me a second. Let me open up my stream on my phone, or my stream manager on my phone, so I can see the chat just in case if there are messages. Okay, cool. So what was I saying? Yeah. Um, I was like, okay, I could actually use these concepts as Gemini was describing it to me. It occurred to me that a bunch of things that are being automated by, or a bunch of things that this framework is actually handling, are things that I would have had to set up by myself. Like, this is exactly what I was trying to accomplish when I was going to create like I was going to create a, hold on. I can go back to that, what do you call it? Yeah, this. So here, wait a minute. You guys can't see that. Shit. Um, Give me a second. Just a second here. Okay, Tmux, attach, T, uh, what is this? Other laptop. Right, okay. Okay, you guys should be able to see it once I switch out of BRB. Here it is. Okay, now, uh, I don't remember which stream I was in, but I was describing all of these, different systems and stuff that I would have to set up. So there would be like hold on, let's go up here. So here you have stuff like the input system, the audio synthesis system, AS, the sender system, and then there's in the other app we have the processing system and the playback system and stuff like that, right? I was setting up systems for everything. I would have had to set up these systems myself, right? As in, I would have had to set up the workflow for the working of each of these systems myself. And I'm so glad that I came across the concept of actors, because I feel like at least um, after getting Gemini's information, after getting information from Gemini about the concept of actors, now I'm able to imagine how this fits into my entire setup, how I can use the concept of actors within my program, and I feel like it's definitely gonna um, I feel like it's definitely gonna improve my workflow, or at the very least, it's gonna make the amount of what am I trying to say here? It's gonna make it less complicated for me to set up what I was trying to set up initially. Yeah, let's just leave it at that. Otherwise, I'm gonna keep trying to articulate what I'm thinking into words, and it's just gonna be a mess. Okay. Hold on. So initially, I had asked the question to Gemini about auto agents and Ractor. I was like, hey, if I give you the link to both of these repos, can you do research on both of them and just tell me what you know? And Gemini was like, yeah, sure. So I did that, and then it gave me nice, concise, uh, few lines of information. It said, Ractor is a Rust actor framework, which is a system for building concurrent applications. It's inspired by a similar system in the Erlang or Erlang programming language. Think of it as a way to manage many small independent workers. And this is important because this is exactly what I was planning on doing. I was planning, regardless whether I was setting up a system or a worker, this is what it was going to be doing. Essentially, it was going to be a worker of some sort, right? Okay, so think of it as a way to manage many small independent workers that communicate with each other by passing messages. The workers in this case are called the actors. Then you have auto agents. Auto agents is a framework for building and managing intelligent agents that use LLMs. It uses Ractor as its foundation to manage these agents. So auto agents is built on top of Ractor, right? Um, it Gemini also mentions that, so the relationship is that auto agents is built on top of Ractor. Ractor provides the underlying actor model that auto agents uses to create and coordinate its intelligent agents. Okay, so this is where auto agents, let's keep it to the side because I was much more interested in Ractor itself. So I was like, okay, hold on, too many terms. I had to be like, you know, let's use simpler terms and all of that. I had to pretend like, hey, I'm very new to the. Actually, I wasn't pretending. I am very new to the concept of actors. I'm not new to the concept of, you know, Rust and programming and all of that in general. But I had to be like, yeah, just simplify things for me. And then it did simplify it. It removed a bunch of the technical jargon, uh, and gave me simple real life kind of examples. And then I told it, okay, yeah, so I have programming experience in Python and Rust, and I've done coding for game dev, data science, and AI and all of that stuff. So now that you've given me this explanation in simple terms. Now I understand the thing. Now you can give me the explanation in technical terms. So now I feel like I would be able to, you know, build up on that concept much better. Okay. Um, where Right. So then it gave me this whole thing of, it gave me a proper explanation of what Ractor is and how Ractor works and all. And through the through this explanation, I found out that Ractor apparently runs on top of Tokyo. Let me see if there's like a different, if there's anything different going on there. Like, are there situations where it wouldn't be using Tokyo? Because at least from what I remember, it was pretty much Tokyo based. Yeah. Now your main application logic or another actor can communicate with this calculator actor using calculator is the example that it was giving me. Um, using its address. So asynchronous tell and asynchronous call. Now because there's async and await and stuff involved, so I was like, yes, okay, this is probably going to be Tokyo based. At some point it did mention Tokyo. Tokyo got brought up, and because of that I was like, okay, before we go deeper into this, I need to properly understand Tokyo. Dude, this is the interesting thing, right? I've done async stuff in C sharp. C sharp has two or three. I don't know if they came up with something new yet again, but like they've had over time, they've had two or three. I believe it was three. Like there was one initially, and then because that one didn't scale very well, then they came up with a much better one, and then because that didn't scale very well, then they came up with a much better one. The final one, I believe, was TAP. I believe it was a task-based asynchronous programming model, and that's what I stuck with. That's what I decided to learn. So out of the box, it's not multi-threaded. That's the important thing here. I'm not really going to go into detail about how the tap model works. I believe you can make it multi-threaded, but out of the box, it's not meant to be multi-threaded. The whole idea there is that it's supposed to be asynchronous, but on the main on the same thread. So you're supposed to be able to start up an asynchronous task, and then whenever the task has to wait for something, if there's going to be some kind of blocking going on there, then you await, and it basically transfers the control out of that async function back to the main calling function, and then you can continue running your entire code until that previous task completes. Once that previous task completes, it'll temporarily transfer the control back there so you can finish that task, like finish the whole cleanup that has to happen there. And then it'll finish that and then come back and continue this again. So that's kind of how async works on that end. And I believe it works in a similar way on the Python end as well. I believe so. I didn't get a chance to go too deep into async stuff in Python either. I have very basic async knowledge, so I'm not really talking about more what do you call it? I'm not really talking about more advanced implementations, but on a basic level, it is also even on the Python end, it's meant to be running on that same thread. The async stuff is happening on the same thread. And this is why, like, because I'm used to the C sharp and Python async stuff, this is why when I came into Rust, I didn't assume that multi-threading would be involved when we were talking about async stuff. I was like, okay, async is different, multi-threading is different. It turns out in Rust, if you're using Tokyo, I don't know about other async frameworks, but Tokyo seems to be like the most famous one. It seems to be the, I think they're calling it the standard. Like that's what's widely used right now. Even a lot of the libraries that I've seen that support async stuff, they are also supporting it through Tokyo. Okay, so when I came into the async side of Rust, I didn't assume that async and multi-threading were going to be together. I assumed that they were different concepts. So you could either go for async or you could go for multi-threaded. But it turns out that Tokyo is designed in such a way that by default it's multi-threaded. Not only is it multi-threaded by default, apparently it also has the ability to just move tasks around. So it can start up an asynchronous task on one thread. Like when you initialize a runtime, the Tokyo runtime, it'll set up a certain number of threads that it can use for these tasks, and each of those threads has its own queue. So so each thread can have tasks queued for it, right? This is where like it becomes really interesting because first of all, just because a task is queued in a specific thread doesn't mean it's going to be stuck there. The Tokyo runtime has this concept of I think it was called work stealing or something. Hold on, let me scroll down here. I haven't copied that specific thing because like that was early on in the conversation, and I'm only able to copy the very last response that Gemini gave, so I can show that to you guys. But I can't show you guys the what was before, so I can only read that out for you. But yeah, I mean, reading it out works just as well. So I'm gonna read this thing out for you because I did have a bunch of uh, questions. But okay, I can wait. Let me go take a look at the answer that was given. So like we stepped away from the concept of Ractor because I was like, okay, and this was like one or two messages later. Uh, I was like, okay, you know what? Let's keep Ractor aside for a second because I feel like I need to understand Tokyo much better before we go into Ractor stuff. Because you're mentioning async await and there's multi-threading being mentioned, and I feel like unless I properly understand Tokyo, I shouldn't be going into Ractor. Um, oh, okay, yeah. So it mentioned I just right now while I was scrolling this thing, uh, I just happened to see this where it mentioned the runtime. Actually, can I export this? If I export this thing, how well will you guys be able to read it? You know what? Wait, I can give it a try. Wait, share Gemini explains Rust. No, Gemini explains Ractor full dot md. Oh yeah, dude. Okay, if I export this as MD, um, and then I open this up in unknown command. What? Oh, I think it's chat share. Yeah, I think it's chat share. Okay, so the conversation has been shared there. I can now open this up and copy the entire thing and then paste it in there. And then I can show it to you guys. So give me a second here. I just need to copy the entire thing. Gemini explains Rust. No, Gemini explains Ractor. Yeah, just a second. I'm opening this thing up. I also need to be a bit picky about what I decide to. Oh, actually, yeah, no, it's going to be. Oh, damn. Okay, I forgot about that. Oh, you know what? No, that's fine. That's fine. So, okay, I asked for this and then it took those actions. Okay, it got that response, and then the model gave me the answer. Okay. User Wait. Okay, okay. Let me just make sure that there's nothing more here because there's quite a bit to scroll through. And then later on, I can just open this up and I think we're good. Yeah, I think we're good because I don't think it did more research after that because it had information on Tokyo already. So I need to decide from where I want to copy this. I think from here is I think from here it's fine. So we'll go from here all the way to the end and copy. I hope that copied. I don't know if that copied. Did that? Okay, I yanked it. Now let's try to open up another thing. Yeah, okay, it's fine. Okay, next. Nope. Let's go back here. Let's create a new thing here. Go into Scratch stuff. NeoVim, Gemini, explains, Ractor, full.md. Open that up, paste, and I think we have the entire thing. Is that it? I hope so. Let me go back to the top. Yes, okay, it's done. Great. So let me just save this, and after that, I can open it up in Frogmouth, um, which is our Markdown viewer. Okay, so now I can show it to you guys here. Right. So this was I did remove the earlier parts of the conversation because I wasn't sure what all information Gemini was giving out there. But yeah, this is our conversation. This is what I was reading out earlier as well. I was like, okay, hold up, too many terms. I have no idea what either of these frameworks do. More details, please. Okay, it gave me all of this information. And then in the next thing, I said, okay, so I do, yeah, okay. So I said, wait, okay, so I do Rust and Python coding. I've done data science, game dev, and deep learning coding. Getting rid of the jargon helped build a foundation for me. Now you can start using the technical terms. I would like to dive deeper in Reactor, in Reactor because this seems interesting. So exactly how are these agents operating? So then it gave me all of this information about how exactly these agents are doing their thing. It gave me some code examples as well. And give me a second here. This was it kept on like it was giving a bunch of very useful information, which helped me learn a lot about Ractor, and I'm definitely going to be using this later on. And dude, I'm actually curious. I'm legitimately curious about whether I would be able to use this in game dev as well. I'm seeing no reason why I wouldn't be able to use it, like to do like specific tasks. Because, dude, the concept of an actor, it seems really interesting to me. Like you are able to spawn this agent that you can program to do a certain task, and this the system that's handling these agents, the system that's managing these agents, that system is built on top of Tokyo, which is an async. I don't know if I should call it an async runtime or an async framework or wait. I think I loaded up Tokyo here. Um, Tokyo. Tokyo is an asynchronous runtime for the Rust programming language. Okay, so Tokyo is an async framework. It's an async runtime. Um, Shit, I lost my train of thought. What was I saying? I was saying that Tokyo. So Ractor Ractor is a system that manages agents, and that system is built on top of Tokyo. Tokyo, which is an asynchronous, it's an async runtime, and Tokyo allows you to do asynchronous programming, but not just asynchronous on the same thread, multi-threaded asynchronous. So I feel like this gives us like a higher level, a very useful higher level way of doing multi-threaded stuff. um, because like I've had plenty of situations where I would I needed to create systems where there would be this thing being done and then that thing being done, and then after that we would have some other thing being done, and each of these things would have to be like we would have to program not just what they have to do, but they're working together, if that makes sense. They're the communication between them. We would I would have to program that as well. And I feel like the concept of actors, it kind of solves that problem. And it's a huge, huge bonus. The fact that a lot of this is multi-threaded by default, because Ractor is running on Tokyo, and Tokyo is multi-threaded by default. It does the tasks multi-threaded by default. Speaking of multi-threading, or speaking of multi-threaded by default, I was talking about something that I found really cool about Tokyo. It's that okay, Tokyo actually okay. You know what? I don't need to like try and remember it. I can just scroll down here and show you what Gemini explained to me, because I asked exactly these questions that I'm now, the that I'm kind of repeating the answers to, the explanations to. I'm kind of repeating them, but all of that is here, so you guys can just read it, or I can read it out. So I was like, okay, I haven't read your entire response yet. I definitely will, but in the meantime, I had some Ractor questions, so I'm dropping them here. So does this mean this whole system carries overhead that could possibly slow down a performance critical system? Or is the overhead for all that work so minuscule that it can be neglected? And then also, you mentioned asynchronous. So all this happens on the main thread. What about multi-threading? Then also, you mentioned one actor can change. Oh, I meant to say one actor can't change another's state. I just realized that I made this mistake here, and this now it makes sense why Gemini replied the way that it did later on. It said that let me correct my statement, let me correct the misunderstanding. What I had actually said was so and so, and then I was like, okay, what's going on? What's going on here? But yeah, okay, it was because I made a mistake here saying you mentioned one actor can. I meant to say cannot change another's state, because that's what Gemini had said, that each of these actors, they have their own state, and their state is a private state. One actor cannot change the state of another actor. Okay. And I was like, yeah, okay, that's fine, but is there a way to share state between the actors somehow? And then here's what Gemini's response was. It said, "Excellent questions. These get right to the core of the trade-offs involved in any concurrency model. Let's tackle them one by one." So then it spoke about the overhead thing. It said, "You are correct. There is overhead. It's not zero, but it's a trade-off for significant gains in other areas. The overhead comes from a few places: message passing and scheduling. Message passing is sending a message. What? Okay, so it's explaining message passing. Sending a message involves allocating the message, putting it into a channel, the mailbox, and waking up the receiving task. This is inherently more work than a direct function call. Okay. Oh, this is message passing, I'm assuming, between the actors. Wait, not even between the actors. Hold on. Yeah, no, in this case we're still talking about actors, so between the actors. And then scheduling. The async runtime, which we'll get to next, has to manage and schedule all the actor tasks. However, comparing this to the alternative is crucial. In traditional multi-threading, the alternative is shared memory with locks. We're going to be learning about all that once we get into the multi-threaded side of Rust. Locks also have significant overhead. Lock contention, if multiple threads try to access the same lock, all but one will be blocked. Waiting. This is wasted CPU time. Okay, then complexity and bugs. Okay, so here it talks about, I believe, race conditions um, and deadlocks as well. Okay, and yes, those are a nightmare to debug because they're race conditions. They don't always pop up, and there are very specific circumstances where they pop up. So it can be hard to like reproduce where exactly the bug is occurring, and that's why you probably won't be able to see the bug that often. Then, the verdict. The actor model trades a small, consistent message passing overhead. I feel like that's important to know. A small message passing overhead for the elimination of lock contention and a massive reduction in complexity. So, for IO bound systems like web servers, databases, or most of auto agents work, which involves waiting for LLM API calls, the actor model is extremely performant. While actually, yeah, that's true because so okay, regardless whether you're sorry, I was looking at something and I lost I got distracted. Wait, hold on. Am I losing the train of thought as well? Oh, regardless whether you are running the LLM locally or if you're having to make an API call to some service where the LLM is actually running, you're going to be doing a certain amount of waiting, right? Unless you have like a super beefy system. And even in the case of a super beefy system, the entire response can still take at the very least a couple of seconds. So where was I going with? Oh yeah, so you are going to be waiting for a certain amount of time, and you don't want to be wasting those cycles. In that meantime, there could be some other work being performed rather than just not doing anything. So this helps in that situation. It says the actor model in this situation, in these cases, is extremely performant. While one actor is waiting for the network, thousands of other actors can be scheduled to do useful work. The message passing overhead is insignificant compared to the I/O wait times. Okay, then for CPU bound systems like pure scientific computing or graphics rendering on a single data set, the actor model might not be the best fit. In those cases, data parallelism models like Rayon in Rust are often more efficient because there's no communication needed, just raw computation on different cores. I guess at some point I'm gonna need to explore that as well. Dude, I kind of like this idea that I just came up with. Well, not just, but like earlier. Because like previously I was like, okay, the I'll just copy the last response because like I don't want to export the entire conversation because I'm not sure if it's going to like include a bunch of extra stuff that it's not supposed to include. It usually won't. Like it's not going to give out information that it's not supposed to, but like actually it is possible. I shouldn't be saying that because Gemini CLI is meant to be like a it's meant to be run it's meant to be running locally, but like the model is not supposed to be running locally. The model is obviously running elsewhere, but the CLI itself is running locally, and do a bunch of you often perform a bunch of tasks and do a bunch of like automation and stuff like that through the CLI. Where was I going with this? Yeah, okay. So the CLI performs a bunch of these operations. It can do file writes, it can do file reads, it can read entire directories, it can do web searches, it can do stuff. It can do a bunch of stuff on your system. Because of which, when it's it can also execute shell commands. All of this is not just automatic. Like it does ask you if you want to give it permission to do that, and only if you allow it, then it does it. But like, this is also why I wouldn't be comfortable just exporting any conversation that I'm having with Gemini, because it might also include some stuff like, for example, maybe it did it tried to read a file, and the file contained a bunch of like sensitive information, or information that I don't want being shown on stream. Or um, maybe it read some file which, again, sensitive information. That just comes back to sensitive information. Maybe there's something that gets shown in that conversation that I wouldn't necessarily want shown on stream, because initially when I'm having the conversation with Gemini, it's not in my mind that, oh, okay, I'm going to be showing this on stream later on. I'm having the conversation with Gemini because I'm doing some research, or I'm trying to solve some kind of problem. So the stream is not really in the back of my mind. I'm not really having the conversation trying to avoid sensitive stuff showing up on the screen, because I know that I'm not assuming that every single conversation I'm going to be showing it on stream, right? Fortunately, in this case, there was very little of that, so I'm a lot more comfortable with showing the conversation, showing the information on stream. Anyways, I've at this point I've forgotten why I was doing this in the first place. Why I was talking about this in the first place. Um, yeah, I think I did mention that. Yeah, maybe later on I can look at Rayon. Um, for now, a lot of the stuff that I'm doing, it's a lot. Um, Tokyo tends to solve the problems a lot more for the stuff that I'm trying to do. But later on, when I do need something like Rayon, then I'll look into Rayon as well. Because there might be some situations where I need to do specific computing tasks. I'm not necessarily always in a situation where I need to set up the system that can do the computation. I'm quite often using other libraries where all of those computation calculations have already been implemented, and I just need to, call the functions. But yeah, okay, anyways, moving forward with this. So the overhead isn't negligible, but it's the price you pay for a safer, more scalable, and often faster concurrency model in the context of complex stateful applications. Then asynchronous versus multi-threading, and this is where it becomes interesting, because like at I think after this, in the next question, I'd said that, hey, I think I need to learn about Tokyo, so teach me about Tokyo now. Let me just scroll down here and see. Okay, hold on. I'm coming from a C sharp tap async and Python async. I'm coming. Hold on. I'm coming from C sharp tap async and Python async. So it's a bit confusing to me here that you're saying that Tokyo also does multi-threading. I feel like I need to learn about Tokyo. Okay, so this is where it starts teaching about Tokyo. We're going to go into that because it gets really interesting. Like, I was excited to know that this system is so sophisticated that not only does it implement something like work stealing, where it can take tasks from other threads queues. So it's going to set up queues that are that are meant to um, process these tasks and do these tasks. It's going to did I say that it'll set up queues? It'll set up queues in each of the threads. So each thread has its own queue, and it'll start queuing up tasks for those threads to complete, right? But then other threads can also steal tasks from other threads. that are currently busy. So like if one thread is it happens to be idle right now, it has finished all of its work and it has no work, but then it sees that another thread has, you know, a long line of tasks, it can actually take some of the tasks from it. And it goes one step further. This is okay, this is what Gemini has told me. I need to read up on Tokyo to confirm that this is actually true. Gemini said that a task that is being, let's say the task has been paused, okay, because there was an await thing going on. So the task has been paused, and it'll be resumed once whatever operation was happening is completed. Then that task will be resumed. The crazy thing is that task can then be resumed from a different thread. Like, that's insane to me. That task can then be resumed from a completely different thread than the thread that started that task. Like, that's crazy, dude. Like, you don't even have to do this by yourself. And this is at least what Gemini has told me about Tokyo. I need to do some of my own tests to, well, test this out. Because if this is the case, then holy shit, Rust and Tokyo, for that matter, have solved the multi-threading problem that a lot of people used to have. Which, I mean, to be fair, a bunch of other languages, they have their async models that have probably solved this problem in their own ways, but this is this is insane to me. The fact that you have stuff like work stealing, you have stuff like, you know, starting a task in one thread, but then you can like pause it and then finish it off in another thread, and a bunch of other stuff that like we'll get into that as we continue reading this conversation. But like that was really cool to me. Give me a second here. I just realized as I'm yapping that it's really quiet here. I need to get a tiny bit of sound going. Just a second here. Also, in the meantime, I guess let me hydrate. Hold on just a minute here. I'm trying to get the audio going in my system. Well, another system. I have no idea why it's taking so long. Okay, I guess that's gonna take some time. So in the meantime, let me just read this. Okay, so asynchronous versus multi-threading. You mentioned asynchronous, so all this happens on the main thread. What about multi-threading? This is a fantastic question and a common point of confusion. The answer is Ractor gives you both concurrency, async, and parallelism, multi-threading. Oh, so we're still talking about Ractor here. Okay. Um, Async with async await. Async await is in Rust is a language feature that allows a single thread to handle tasks concurrently. When a task reaches a point where it has to wait, example for a message to arrive or for a network request to complete, it yields control, allowing the thread to run another task. Okay, this is highly efficient for juggling many I/O bound operations. Then the runtime, that's so hard to say, parallelism. The async code that doesn't the async code doesn't run itself. It's executed by a runtime. Ractor is built on Tokyo, which is the most popular async runtime in the Rust ecosystem. Tokyo manages a thread pool, example, one OS thread per core. When you spawn an actor in Ractor, you are creating an async task. The Tokyo runtime takes that task and schedules it to run on its thread pool. It is free to move that task between threads as it sees fit to balance the load. In short, Tokyo distributes your many actors across multiple OS threads, achieving true parallelism. On each of those threads, the async mechanism efficiently runs many actors concurrently. You get the best of both worlds. Then it spoke about sharing memory between them, and it gave some useful information. We're not going to go too deep into this because it's not really that important right now. It was just a little bit of a doubt that I had. I was like, okay, how exactly do we go about? Because there would be certain situations where I would want the state to be private amongst the actors, or rather, I wouldn't need the state to be shared amongst the actors. But then there are other situations where I would need some kind of state to be shared, like maybe, I don't know, finding out if an actor is currently busy, or finding out if a specific work that it was supposed to be doing is done, or something like that. There could be any situation. Okay, so then I asked it to teach me about Tokyo, and now we jump into Tokyo. So that's a perfect point to pause on, because this is a key difference in how async is commonly implemented and used in the Rust ecosystem versus Python or even C Sharp. Your intuition is correct, and understanding Tokyo is fundamental. Let's break down Tokyo, the job of an async runtime. First, let's separate the language feature, which is async await, from the library that makes it run, that is the runtime. Async await is just a way for the compiler to transform your function into a state machine called a future in Rust. This state machine can be paused or yielded at an await point and resumed later. Okay, the future itself does nothing. It's just a data structure. You need an executor to actually poll it, run it until it yields, and know when to poll it again. This executor, along with timers, I/O drivers, and task scheduling logic, is what we call an async runtime. Python's async I/O is a runtime. C Sharp's TPL has its own runtime components. Rust has a few, but Tokyo is the de facto standard. Okay, then Tokyo's model, multi-threaded work stealing. This is the core concept you're asking about. Unlike Python's async I/O, which typically uses a single-threaded event loop, Tokyo's default runtime is a multi-threaded work-stealing scheduler. Let's use an analogy. Imagine a team of 8 workers, your 8 CPU cores. The thread pool, when you start the Tokyo runtime, it spawns a pool of OS threads, typically one for each CPU core. These are real parallel threads. Spawning tasks. When you call task.spawn, you are not assigning the task to a specific thread. You're handing a new piece of work, which is a future, to the runtime's global queue. Okay, then local queues. The runtime gives each worker thread its own local queue of tasks. A thread will primarily take work from its own queue, which is very fast and avoids coordination overhead. The work stealing magic. What happens if worker 1 finishes all the tasks in its local queue, but worker 2 is still swamped? Instead of going to sleep, worker 1 will look at the queues of other workers and steal a task from them. This is what I was talking about. This was, dude, this was crazy to me. Like the fact that this is just like an automatic thing happening now, that's crazy to me. And I can kind of see why a lot of people tend to go towards Rust, if especially if they're trying to write like performance critical applications that'll be, multi-threaded by default and stuff. Okay. Um where was I? Yeah. This is how the work stealing hold on. This is the work stealing part. It provides automatic dynamic load balancing. Idle threads find work to do, ensuring that all CPU cores are utilized as much as possible. Then, handling I/O. What happens when a task on worker 3 needs to wait for a network socket to be readable? The task yields, worker 3 doesn't block it. No, worker 3 doesn't block. It immediately drops the task for now and picks up the next task in queue. The Tokyo runtime tells the operating system, let me know when this socket is ready. When the OS sends the notification, the runtime makes the waiting task runnable again and places it back into the queue to be picked up by any available worker thread. This is what I was talking about as well, where I was like, okay, you can start the task in one thread and it can be paused there, but then it can be resumed in some other thread. Like that's, dude. I mean, okay, there might be some overhead, but like I'm assuming that that overhead gets managed efficiently by Tokyo. I do need to do research on what the overhead is. Though, I mean, I feel like, I'll get the answer for that. I'm still going to do the research, but I feel like what I'm doing research on there is something that is already automated. Like that's not something that I need to do manually. That is all being handled by the runtime, regardless whether so whether the runtime decides to make that same thread resume the task or move the task to a different thread. Um, I feel like all of that it's not really in my control, but I'm still gonna look. Well, okay, it's less about it being in my control and more about like if this is already being automated, then the people who are currently, building this system, they have probably come up with the best solution possible, the best workflow possible for this, the most efficient workflow possible. So I don't really need to worry too much about, it being inefficient. Um, I'm just kind of gonna have to be okay with the fact that there might be a tiny overhead, if that at all. Okay. Then we were here. I don't remember if I finished reading this part. I think I did. Well, kind of. Yeah, yeah. I so okay, here there was a code example. And okay, dude, for today's stream, I was actually planning on giving Gemini a prompt, which I'd even opened up. Where is it? It's somewhere back here. Yeah, I'd open up this thing just so I'd open up this extra Gemini instance just so I could create the prompt for Gemini to teach me about Tokyo, specifically about Tokyo. And I was going to tell it, okay, create this simple syllabus for me, and then we can go through it chapter by chapter. And by the end, hopefully, I will know all about Tokyo. Because I feel like I need to learn about Tokyo not only to be able to set up my own stuff through Tokyo, but more importantly, just so I have an idea of what I'm doing when I'm using other libraries that are built on top of Tokyo, because there's a lot of libraries that support async await stuff, that support async programming in general through the Tokyo runtime. So I need to learn Tokyo. Okay, so here it gave this example where in the code um, the code was basically spawning a bunch of tasks, and within the task it would like print out the current thread ID, and so through this it was showing in the output down here that this is this is how it's starting a task on like whatever thread is available, and then as it's starting more further tasks, it starts the task on whatever thread is currently available. So like you can see thread ID 3, for example, it was available previously, and then thread 4, then thread 2, thread 5, and then thread 3 again. And then there's more repetitions like thread 2 and thread 4 and so on. And then it also mentioned that tasks can end possibly on different threads than they started on. The key takeaway is that the tasks are running on different thread IDs. This is Tokyo using its thread pool to execute your async tasks in parallel. Okay, right. So then I asked another question. I was like, well, I gave it another prompt. I said, wait, that's wild. It's also wildly efficient. So the runtime can just move tasks from one thread to another as it sees fit. And even a paused task can entirely be moved to another thread to finish. Also, what if I have a situation where, so okay, this was something I'd gotten from another, I think it was from C sharp. I believe it was from C sharp because like in C sharp, I think it was in the tap model. You had like you had ways to create dependencies. So like one task depends on another, and it won't run until that other task is completed. So it won't run until you've given it the result from the other task, or just in general the other task is completed. It's not about the result, but like in general, until the other task is completed, this task is not going to run. Or maybe you want to run multiple tasks in parallel, like running it in a for loop or something like that. It had like different ways of doing that. So I was like, okay, what if we wanted to create a similar system here? Like, okay, one task depends on another, or one task requires two other tasks to finish before it can start. Um, and yeah, apparently it is. Right. So um, first I think it dove deeper into the whole work stealing thing. Yeah, I don't think I finished reading this whole thing because I'd gotten busy doing something else. Um, but dude, okay, I need to, now that I've gotten interested in this, I need to finish learning Tokyo and then start learning Ractor and then continue. Holy shit, dude. There's so much stuff to do. I'm not gonna, if I keep getting distracted with more stuff, I mean, to be fair, it's a good thing that I'm getting distracted with this because I'm definitely going to be using this for something. But like, holy shit, I need to finish learning the basics of Tokyo. I need to then learn the basics of Ractor. I need to then continue learning the basics of Rust, which at this point we are going into more advanced stuff in the Rust basics. Then I need to start working on the AI voice app, or the multiple components of that app. And then we need to get back to fucking data science, dude. Holy shit. There's also the gen, not the gen, the agent, the agent, the AI agent course. We need to complete that. We need to continue that. We haven't gone past day one yet. Um, yeah, yeah. Okay, hold on just a second. So, um, anyways, let's continue reading this. Right, task migration across threads. Um, so I'd asked one or two questions there, and it said, yes, absolutely. This is a core feature of Tokyo's work stealing scheduler and one of its main advantages. Here's why it works. Futures are send. I believe this means that they implement a send trait. Yeah, it mentions that. In Rust, for a future, your async task to be moved from one thread to another, it must implement the send trait. This trait indicates that it's safe to transfer ownership of the type across thread boundaries. Async functions in Rust produce futures that are send by default, as long as all the data as long as all the data they capture and use is also send. This is usually the case unless you're holding on to raw pointers or RC types, which are explicitly not send. Then state machines. Recall that async functions compile Recall that an async function compiles down to a state machine. When a task yields at an await point, its current state, local variables where it needs to resume, is packed up. Oh, when it yields at an await, so when it hits an await point, then its current state is packed up. Okay. This packed up state is then placed back into a queue. Any worker thread can pick up this packaged state from the queue and resume executing it. It doesn't matter which thread started it or which thread was running it previously. Work stealing in action. Thread A starts task X. Task X performs some work and then hits an await point. Task X yields, and thread A goes to process other tasks. Later, the socket becomes available, and the Tokyo runtime marks task X as ready to run again. Task X is put into a queue, and thread B, which just finished its current tasks and is looking for more work, perhaps even stealing from thread A's queue, picks up task X and resumes it from where it left off. This dynamic reallocation of tasks to available threads is what makes Tokyo so good at maximizing CPU utilization and adapting to fluctuating workloads. Then, handling task dependencies. Okay, this, I'm going to have to read this by myself so I can get a better understanding. So it mentions that there's stuff like join and select and maybe something else as well. I need to, yeah, I'm gonna read this by myself later on. Give me a second here. Okay, hold on. I think I caught this person at the wrong time. Yeah. Um, let's go with someone else. Okay, just a second here. Okay, hold up. Okay, you know what? We are gonna go to this person's stream. So this is someone called Espen Epic. Um, yeah, we're gonna go hang out in this person's stream. They are doing something biology related, I believe. They're also doing co-working and studying. So yeah, we're gonna go check out their stream and we're gonna hang out for some time there. But yeah, that's gonna be it for today's stream. I hope I'm able to start streaming earlier tomorrow because I was supposed to start earlier today, but then I lost almost an entire hour because I had to restart my laptop and then my laptop refused to work properly and I had to restart it again and then it takes a bit of time to set up after I've restarted. So like it's like it was a whole mess. I would have started so much earlier if I could. But yeah, dude, that's gonna be it for today's stream. Hopefully, I'm able to stream again tomorrow. That being said, I hope you guys have a nice day, and I'll see you all next time. Peace.